So some of you came and told me at Fika that I went way too fast. I apologize. I thought it was all boring and obvious. Maybe we'll go a little bit slower in this one. You'll start seeing the patterns are identical, right? Because you're using the same type of pipelines. So I found this talk by Mira quite cool. It was last year. So this is her GitHub. Mira Lakhani, I think she's. So I highly recommend you watch this video later because this is a proper. How would I say? So this is like a more serious data science project, right? Because what she's doing is setting up a Cassandra Cassandra store, which is a key value store.
Time series and prediction with the Android, Spark, and Cassandra.
Yeah.
But before starting, I just want to warn you, you may hear some awkward words during the presentation. Don't worry.
So anyway, I will let you watch this nice show, but what she's doing is getting her teammates to take accelerometer measurements from their cell phones when they're sitting, walking, jogging, and things like this. And they share the data, and that data actually streams into, I'm not sure if it's using Kafka or what to, some queues to collect it and store it in Cassandra, and then she's using Apache Spark connectors to read from the Cassandra database, and then doing machine learning for activity recognition. So purely from the accelerometer readings, she wants to predict whether these guys are sitting or standing. So she does all of this live. It's a pretty kick-ass presentation. So anyway, I'll let you watch it later. So this is actually data set from her. Let's see if this will work. So we have to first make sure that this data set is available. So let's see. So this won't be generally available. Well, okay, you won't know this because that's just. Okay, so there is no file, right? So we have to first of all doubly get the data. So let's just go downstairs here. There should be some commands on. So I just put this on my domain, GoDaddy. So you can just download it and so I just want to move this file. Let's see. I may have to do this first. Create this directory. Actually, let me make sure this directory. So db utils.fs.ls. I think I can just do data sets. Let's see what's in here. Add display. Okay, there is no directory called SDS. So what I have to first do is make this directory. Okay, so now I think I'm good. So now let me just move the file from the driver to this directory. And so now I should have this file. So it has 93 or 931,349 is the size of the file. Okay, so everyone should be there. Okay, so let me wait and make sure, so I'm just created a directory and dumped this file there. Yeah.
Where did you get the file?
Oh, sorry. I just doubly got it from my homepage. I just already asked Amira's permission and I put the files here. So you want to, so we just went into shell and then just. So yeah, this is step one, and then here I'm just print working directory and listing the files there. And I notice that training.csv has come. You see? So if you do the wget and do this, then you should have this file training. And then I just, I just want to, this is the third command you want, right? So this is just making this directory first. And then I'm just moving that file from my local driver to the distributed file system. And
sorry, where did you find the link for the file, the CSV file?
oh, so it's not there in the bottom?
Do I have an old version of it? Or?
So you don't have this?
I can't see the command number from here, so.
Oh, command 27?
Oh, okay. Sorry.
Yeah, that's good. Should definitely stop. if you're stuck, otherwise I'm just gonna go, right? Yeah.
All right. Sorry.
Yeah. So, but when you watch the video, like, Amira is doing all this live, like, people's measurements are already going on the cell phone live and stuff. It's really, yeah. So I've just taken her data and then just put it here. Okay, so in the end, you should be able to just see this. Okay. So let's just, so once you've done this, you only need to do that once for your community edition, right? So then the data will be there. Now I'm just checking out this RDD, back on command 5 on the top, and I'm just making sure I can read the first 5 lines. So if you notice, the first column is user ID and activity, timestamp as long, X, Y, and Z. So these are the X axis, Y axis, and Z axis of the for the accelerometer in the cell phone. Okay, so now, so if you look at it, user ID, user 001, his activity or her activity is jumping. And then this is the timestamp as long, which is, I guess, the number of milliseconds after midnight, January 1st, 1970, something.
Yeah,
Something like this. So, and then this is X, Y, and Z, right? So this is basically. So if I list this, there will be several other users, and they'll be doing different activities, maybe sitting, standing, and so on. So this is I'm just using sort of code that'll work in older versions of Spark as well. So I'm doing SQL context, read, and then because it's a CSV file, I'm simply using this format. I'm just saying header is true. I'm saying in first schema automatically, which means it'll actually read the file twice. So this is something you want to avoid. If the file is way too big, then you don't want to read it twice generally. So for that, you would actually have to know the schema of the file, and then if you know the schema, then you can write, case classes, for example, and create a schema. So when you read, you can just read it directly with the known or expected schema. So now just printing schema, and that's what we have. So it automatically cast it nicely into doubles, X, Y, and Z, and long, and the other two are strings. So I'm just seeing the same thing now display. So this will show me the first 1,000 rows. So I can sort of go down, and let me see if I have some other activity. Remote. There, user 3 is also jumping, and So I can just count, so 13,679 rows. And so now I have user IDs. There's 6 users, right? 001, 7 users. So these are 7 different friends of Mira's, I guess. And then I'm just doing select activity distinct show. So it's either they're sitting, walking, jumping, standing, or jogging. It's 5 discrete classes. So we want to build a discrete classifier, right? A classifier. So if you look at the picture and the scatter plot for just the X, Y, and Z values, and then put the keys as these 5 things in different colors, you see this kind of pattern, right? So remember, you can do this plot options thing, and so all I've done is values are X, Y, Z, and the activity is the keys. So you can see that there's a lot of overlay, right? It's hard to tell sitting from jogging along Y and X, okay? So we definitely want to do some kind of feature engineering. We cannot directly start messing with this information, right? So what we have to now think about is the data is actually coming from these 7 individuals as they are actually doing something with the cell phone. So they're kind of jogging for a while, and then they stop, and they're sitting for a while, and whatever, standing for a while. So there's a time component to all of this, right? So you want to try and exploit this time structure in your feature engineering. So we can kind of make this sort of Markov process assumption. By this, all I mean is what happened in the recent past affects what's about to happen, right? Or what's happening right now. So if I was running for the last few milliseconds, I'm still running, right? That's kind of the assumption. As long as the users are not instantaneously sitting and walking and jogging, then this is a reasonable assumption. So we want to somehow look into the moving windows now, right? To look at the information in the recent past. Okay, so for this, we have to get into windowing functions in Spark. So you haven't seen this yet. This is a very, very powerful SQL, Spark SQL functionality, moving windows. So you can actually have various operations done on a sliding window in your data frame. So we're going to import some window functions, so expressions.window and SQL functions. These things in SQL functions. So what I'm going to do is create a window size. I just played around with this, so I didn't magically come up with 10. I just played around with the data, and 10 was reasonable. So if you also look at the timestamps, for example, right? So here's 85158, 85222, 85287. So these are in milliseconds, right? So this is, So this is every 100 and so, every 1,000 milliseconds or so, right? There is maybe this is every second information. So by looking at the last 10, it's actually just very quickly at what they were doing in the last couple seconds. So now what I do is window.partitionBy. So this is a method. So I take my my window and I partition the window by user ID and activity, right? So I have these 2 columns. So it'll be user ID specific and activity specific for that user. And then once I have picked those 2 columns to partition by, then I actually want to order by the timestamp itself, because because it's an RDD, things are just going to be in random order if you don't specify, they're just distributed. So I actually want to order by the timestamp ID, so I have a actual temporal information. So once I've done this, what I have is a user ID activity specific timestamp information. So now the X, Y, and Z, the accelerometer readings are sensible. They're actually what user A was doing, jogging, and what was the 3 readings for that. So now I do my rows between negative of my window size to 0. That means 0 is now, and I go up to minus 10 units into the past in this ordered timestamp thing. So is that clear what the window specification is? So then okay. So you have to get into Amira's GitHub and her talk to figure out what her intuitions were. So she's doing quite a lot, and I found out that you don't need all of this magic actually to do almost as good. But so what she was doing is she was looking at the mean, okay, over the window, mean in the x direction, mean in the y, and mean in z. That's good, right? It'll give you a sense of how what was the acceleration along x, y, and z, the mean acceleration in the last 10 time units, whatever you were doing. So that's good. And then she was also looking at the resultant, which is sum of the squared, so this is the Euclidean distance divided by, and the mean resultant. And she was looking at other things as well, b minus the mean for each b in x, y, and z. So this is the absolute deviation from the mean of x, from the mean y, mean z. Mean absolute deviation. So these are all various summary statistics of the immediate past. This one was squared deviation from the mean, variance along x, variance along y, variance along z, standard deviation along x, y, and z. Okay. So for each of these, I can simply apply. I can basically get this huge data frame. So let's do this. Oh, what happened? Mean not found. Oh, did I not? Keep that. Okay, all right. It's good to import stuff. Okay, so now, okay, I don't want to pretend like all of this came out of nowhere. This was a couple hours of my time. Okay, but let's just jump and look at this, right? So now you see the point is when we simply looked at the raw x, y, and z accelerometer readings at every instant of the activity, we couldn't see anything. But now when we sort of have this Markov perspective and look at what happened in the recent past, even these simple summaries are allowing us to look at nice partitions. And this should make physical sense because when you're jogging versus sitting, right? You very x, y, and z should be quite close to 0, right? There's going to be 0 acceleration in all 3 coordinates you're sitting versus jogging. So those kinds of things are basically what are picked up here. And I played around with all various combinations, and I just found that just means and the standard deviations was actually pretty reasonable enough to get these colors to partition separately, so we can start throwing some trees at it. Okay, and it should make some kind of sense because standard deviations tell you quite a lot about how much variance was there, and the means tell you about whether you are accelerating or sitting still or whatever. Okay. So then I'm just doing a random split now, just training and test, and just because that's what she did. And then we have to get into what random forests are very briefly. So let me just pull up this gentle introduction to random forests. So let me just show you. So the main idea is this one, right? So what you do is you take all your data in the random forest, and then you take a random subset of the data, okay, both row-wise, so you only take some rows, and also only some columns. Okay, so you won't use all the features every time. So you take a random subset of the data, and then you would build a tree for that random subset. Right? That becomes one of your trees in your forest. So forest is just a bunch of trees. So it's a very different idea, right, compared to just going all the way down to maximal depth with your decision tree, or allowing lots and lots of stubby trees in the gradient boosted world we just saw. This is another method, and it comes from this idea called bagging, which is basically here. So this is one of those. Yeah, so it's this idea of tree bagging, right? Bootstrap aggregation. So you basically take a subsample of the data, and then you use that subsample to create your tree, and then you aggregate it. You somehow consult all the trees, and then find the average value they tell you, and then use that as your prediction. That's the So you wanted to know some difference between
very suitable for like what's a good use for a random forest versus a gradient.
Oh yeah, right. So yeah, so he was asking this question about, because I think computer science or ML guys sometimes get into little wars, like my model is better than yours, and I don't want to get into it, but you guys have the principled way to let the models fight fairly, because remember, we can set up an evaluation metric, say root mean square error for regression, and then you can actually do hyperparameter tuning, the right hyperparameters for that model, and get the best model in that class, and do the same for another model. And then you can just see how well, gradient boosted trees versus random forests fit your own data, or linear regression, right? So you can let them fight. And I don't think there will be generally a clear winner for every case, right? It's going to be dependent on the data set itself. So that's okay. So random forests are essentially what Amira throws at this in her talk. So I just tried to do the same. Basically, I try to watch a YouTube video and try to replicate everything. Okay, that's all I've done here. So let's go through this slowly. So what I'm doing here is, remember I need the string indexer because this is a classification problem, just like our digit classification problem. We're not in the regression setting anymore. And we need the vector assembler to say what input columns we're going to choose, right? So I'm saying my input columns for my vector assembler simply is this array of mean x, mean y, mean z, standard deviation x, y, and z, right? These things I pulled out using my windowing SQL operation. Now I'm going to say that's my input column for my vector assembler. And the vector assembler is going to take that as input and produce my output column to be features. Okay. This is the stuff you were asking, right? So I could have said anything else here, right? I could have chosen the resultants, and I did play around. So I think Amira does a few more things. I actually forgot if she does the same thing or not. So you can play around with that as well. Yeah, and the nice thing with random forests is, it will drop some of them anyway at random. So, okay, so yeah, so my transformer, you see, so this thing is now itself built of several steps in an array, and it has the string indexer. What does a string indexer do? It takes, it has an input column, which is the activity column. And then it's going to take that activity column with jogging, sitting, and so on, and then convert that into the output column labels. And these things are already strings, but it'll use the string indexer to turn it into a label. The format that this algorithm needs. Okay, any classifier will need this string indexer method. And then yeah, so now I have basic transformations. I have my features ready. I have my label ready. And then I just have my immutable RF as my random forest classifier, and the random forest classifier has a lot of parameters, methods. So basically setting the label column, setting the feature column, label features, and I'm setting the number of trees to be 10 here. I'm setting the feature subset strategy to be auto, so some automatic. So you can even get into, controlling how the feature subsets are actually chosen for each tree. So I'm just taking the default here, and so this is this impurity index. You remember when we talked about the San Francisco, New York thing? I said there is some notion of homogeneity that gets measured, like the different labels in the same cell. So Gini is one. Gini impurity index is one measure. So anyway, set max depth is 20. This is again a parameter for the depth each tree is allowed to go. So max bins is this one, just to coarsen things. It will matter here. Well, I actually don't know, it may matter. But so this is yeah, how I'm coarsening my features. And then my set seed, just whatever, some arbitrary seed I choose for the randomizations. So I can replicate it to pick different features. I can replicate it by setting the seed. So and then in the end, I just have my model. I just take my pipeline object and then I do set stages. And so I can apply the RF method to the transformers. And so the transformers will take the, transformers will be applied to the random forest. And what I'm fitting in is the training data. So the training data will basically go through the transformers and then be plugged into the random forest model. So this ran, it took 4 minutes and 47 seconds. I won't hit this now. And in the end, you can compute accuracy like this, which is, I'm basically asking what fraction of the predicted activities agreed with the actual activities. So, and this one gave almost 98% correct predictions. So, pretty happy with this. And this is essentially the output of this. So, if my activity was jumping, my label was 4, and my prediction was 0. If it was walking, it was 2 and 1, 2 and 1, so these things were wrong. Oh, it's all wrong. What's going on? Maybe I didn't evaluate it.
So you fields are wrong.
Yeah, they're displaying just the wrong.
Yes.
I'm just. Oh yes, thanks. Yes, thank you very much. Not okay. Yeah, good. So when I actually do this, I know what I'm doing, right? But I just forget a lot, which I hope makes you brave, right? It's just. Anyway, I think her talk is really good. Yeah.
How did you choose the hyperparameters when you create the model? Like you have state tree number 10 and this kind of
You mean the features?
yeah, in this case, when you the random forest thing, when you create the model,
Yeah.
when you train the model.
Right. I mean, here I don't even have any cross validation or anything, right? I'm just like, boom, I'm just saying, this is the maximal depth, this is the max bins. I was happy, 98% I'm happy, right? I stopped. But ideally, in this case, you could do hyperparameter tuning, just like we did before. So then maybe I would play around with max depths, and I may even play around with the set feature subset strategy, different strategies if you look at the docs. So those will become your hyperparameters, right? So maybe different strategies and different depths. Depths are natural hyperparameters for trees, right? And for gradient boosted trees, maybe even the number of trees you're using. You see it already blows up, like 3 for hyperparameters, and even if you have like 5 each, that's 5 is at 25, 25, 5 is at what, 25. So you have to do 125 reevaluations of all this. And of course, if you do, are we going to use cross-validation for this? Say 3-fold cross-validation? It adds up, right? So yes, you would want to do it. Say if I had gotten only 60 or 70 or 80% accuracy, I would definitely try to tune the model. But here I just got lucky. Actually, I didn't get lucky. I actually watched Amira's video and I just chose the hyperparameters she used. I'm sure she spent a lot of time. She talks about how she wasted a lot of time probably. So yeah, this is magic, but it's already like kind of pretty optimally chosen. And typically you won't know this, so you'll have to play around. Any other questions? So is this a little bit better? If you go back and look at the other notebook, I think it'll make sense. It's because I don't want to spend too much time on syntax, right? But I also don't want to go too fast on syntax. Yeah.
How do you usually variables that are just like correlate? Because I mean, in this one there's four.
Yeah.
You take different variable and then you just give another result.
Yeah.
So how does it work when you have like super correlated variables? Then they all say the same thing.
Yes, so I think in the random forest, like it'll be good, right? Because these hyper, correlated variables, when they get dropped, when one of them gets dropped, it shouldn't affect any information that's left, right? So in that sense, it could be good. But also, like we hand-tuned the thing here, right? I just wanted the mean in X, Y, and Z for the accelerometers, and also the standard deviation. That intuitively captures a lot, right? How fast, what was the acceleration on average on each coordinate, and what was the, because when you jog versus walk, I think there are standard deviations are different if you look at the picture. Okay.
I have a question.
Yeah.
Say you wanted to now deploy this and do the online streaming application.
Yeah.
Can you just take this model object and do some data, some Spark streaming buffer or something, or how do you connect this? How do you...
Oh, right. So, well, we have to do streaming first, right? So I think my next topic is streaming.
Okay.
If I'm not wrong. So I'll introduce you to basic concepts of Apache Spark streaming. And then we basically have this, I have to figure this out in 2.2, there's slightly different frame of discrete streams. So these are like some kind of small RDBs. And then, and then, you can, once you've built the model, in Amira's example, what she does is I think she has some kind of queue, like Kafka queue or something, that'll take the client's accelerometer measurements and stick them into something like Cassandra, some key value store. And then this model can be just turned loose on that, and you can start serving the predictions back. Okay. Or you can, in fact, probably even directly plug the model into the stream. So we'll get into that soon.
So I'm wondering a bit about the sliding windows. Will those sort of carry over to the buffer, so do you do something different?
I see what you mean. No, right. No, so in this case, we train the model on all of this historical data, right? So we statically inferred the model, and then we're serving predictions from that. So yes, if people are, if the culture changes quickly and people are jogging in a weird way, like every few hours, then we'll be screwed in this. But there are ways to actually, in fact, if you look at the MLlib library, there's actually streaming linear regression, streaming k-means. So you can directly start working with streaming variants of all of this. In fact, a lot of the neuroscience data is all using streaming k-means and streaming linear regression because they're making movies all the time, and so doing some kind of models on the go as the data is streaming at you. So we can do that. I mean, we'll have to first learn streaming first.